Welcome. Today we will discuss direct vector control or feedback vector control. So, as we discussed in last class, we have direct vector control or feedback vector control, then indirect and feed forward vector control. In direct vector control, in all these vector control, we have to generate unit vector for vector orientation. In direct vector control, the unit vector, you know what is unit vector? Unit vector is e to the j theta e. So, it has cos theta e and sin theta e, that is theta e angle is required. So, unit vector is generated from rotor flux components rotor components means stationary reference frame components psi alpha r and psi beta r, stationary reference frame components of psi r. So, rotor flux components obtained from direct measurement of air gap flux and adding rotor leakage flux to it, or by estimating rotor flux components using voltage model or current model from the sensed or measured variables like stator voltages, stator currents or speed. So, as I mentioned voltage model and current model. So, voltage model is used to estimate the rotor flux components from sensed stator voltages and stator currents. And another one is the current model. Current model is used to estimate the rotor flux components from sensed stator currents and speed. So, we will draw a vector control scheme, direct vector control scheme. We have a comparator which takes the reference or command value of the rotor flux psi r hat and estimated or rotor flux psi r, and the flux error goes through a flux controller, and flux controller output is the command value of the flux component of the stator current IDS star. Then we have another comparator which compares the actual rotor speed with the reference rotor speed omega r star, and the speed error goes through a speed controller, and output of the speed controller is the torque component of the current stator current command value IQS star. IES is the stator current. It has two components, flux component is IDS and torque component is IQS, and stars are the command values. So here all the time flux controller output generates the command value of the flux component of the current IDS, and speed controller output, because speed is controlled by the torque, speed controller output is the IQS star or command value of the torque component of the current, or in some cases speed controller output is the torque reference, and then there will be torque sensing and feedback, and there will be torque error controller, and torque controller output is the IQS star. The torque controller is in inner loop of the speed controller. So, from this IDS star and IQS star, we have the DQ to 2 phase. DQ is DC. So, DQ to 2 phase alpha beta transformation. And after the transformation, we get the stationary reference frame components. Flux component is I alpha S star and torque component is I beta S star, stationary reference frame components. Then we have 2 phase, that means alpha beta to 3 phase, that means A B C transformation. Which gives the command value of 3 phase currents IA star reference value, IB star 3 phase current commands IA, IB, IC star to the voltage source inverter. Voltage source inverter gets the DC value, DC voltage input and the command value of the current and generates the same currents IA, IB, IC and feeds it to the motor M, induction motor. So, we have a voltage model estimation, voltage model used for estimating the flux components and hence generate the unit vector cos theta E sin theta E unit vector and also estimate the rotor flux psi r hat using the sensed currents and sensed voltage. So, at least we require 2 currents because it is a 3 phase system, 2 currents are sufficient. So, let us write IA, IB 2 currents and V A, VB 2 voltages are required. 2 voltage sensors and 2 current sensors will be there giving feedback signals to the estimation block which estimates the unit vector and rotor flux psi r. And then we also have a speed sensor or shaft encoder which gives the output the estimated speed omega r hat. So, this is the direct vector control scheme with rotor flux orientation. So, in this direct vector control scheme just shown, the principal vector control parameters which are the command values of the flux component and flux torque component of the stator current ID star and IQ star. Parameters are obtained from a flux controller, as you have seen in that, from a flux controller and speed controller, as you have seen in this figure, or torque controller. Respectively. So, the flux controller generates the command value of the flux component of the current ID star and torque controller generates speed controller generates the torque component of current command IQ star. One, that is one possibility. Other possibility is speed controller generates the, you can see here, I am just drawing that. So, another scheme is you have the reference speed omega r star and actual speed omega r or omega r hat. Then you have a speed controller output can be IQ star, command value of the torque component of the current, as I have shown in the previous figure, or speed controller output is the command value of the torque Te star. Then there will be a comparator, so comparing the actual speed torque which is estimated or sensed, that is Te from the command value of the torque generated from the speed controller, and this torque error goes through a torque controller to generate the command value of the current IQ star. So, here torque controller is inside the speed control loop. So, that is extra controller is used for better performance and high performance. Otherwise, speed controller output can be also command value of the torque component of the current. So, as indicated in the previous scheme of direct vector control, voltage model is used. Or alternately we can use a current model, both are possible. So, to obtain the rotor flux components, that is psi alpha r and psi beta r from stator voltages, and stator currents using the voltage model, or stator currents and speed using the current model. So, next we will draw the phasor orientation. This is the alpha beta stationary reference frame, beta axis and alpha axis, the stationary two phase reference frame, and here we have the rotor flux component psi alpha r and rotor flux component psi alpha r. These are the components of rotor flux psi r, and we want in vector control entire rotor flux should be along the d axis, no flux along the q axis. So this is the d axis and q axis is at right angle to d axis. This dq reference frame is the synchronously rotating reference frame which is rotating at synchronous speed omega e, and this vector is the rotor flux psi r which is same as psi d r, because d axis is along the rotor flux psi r equal to psi d r. So, we have rotor flux psi r equals to psi d r, no flux along the q axis, psi q r equal to 0. That is the essential of vector control. Entire flux should be along the d axis, no flux along the q axis, psi q r is 0. So, and we have the d axis stator current I d s which is same as the command value, and also we have I q s torque component of the stator current which is same as torque component of command value. So, I d s is the flux component of the stator current which is responsible for producing the flux psi r. So, because I d s only decides the flux, it is in the same direction as the rotor flux psi r along the d axis, and along q axis torque component of the current is there, and we have psi q r equals to 0. Okay. So, this is the angle, because reference frame is rotating, this is the angle theta e, and also this is the angle theta e. So, that omega e is the synchronous speed, that is the speed of the reference frame, that is d theta e by dt, and e to the power j theta e which is cos theta e plus j sin theta e is the unit vector which gives vector orientation, you can say. What is that vector orientation? So, what is that vector orientation? Flux component of the stator current I d s is along the rotor flux psi r and IQS is perpendicular to it, orthogonal to it, also psi QR is 0. This is the vector orientation. So this is the diagram for phasor orientation. And essentially it relates all the terms like the stationary reference frame components of the rotor flux psi alpha r and psi beta r to the synchronous reference frame components psi dr and psi qr, and relation between the torque components of the current and flux component of the current. This phasor orientation is essential to obtain the vector control, and mainly in vector control the d axis is aligned along the rotor flux psi r, so that psi r is psi dr and psi qr is 0. You can say psi qr or psi qr hat is 0. No flux along the q axis, total flux along the d axis. So, in that case this unit vector theta e as given in indicated e to the j theta e is the unit vector which makes it possible to give a ride of IDS, flux component of the stator current, along the d axis, and torque component of the current IQS orthogonal to it. This is essential and possible only through the vector control. So, from that vector phasor, from the phasor orientation diagram, as you can see, psi alpha r is psi r hat cos theta e, and psi beta r is psi r hat rotor flux into sin theta e. So, this gives psi r hat is square root of psi alpha r square plus psi beta r square. So, in other way we can write the unit vector components cos theta e is psi alpha r by psi r hat, and sin theta e is psi beta r by psi r hat. So, this is the unit vector which gives vector rotation and a ride of current IDS, which is the flux component of the current, on the d axis, or rotor flux axis, and current IQS on the q axis. At this condition, that means vector orientation or field orientation at this condition of field orientation, there is no flux along the q axis. Psi qr is 0 and psi dr equals to psi r hat. So, with that torque, double lap torque T e is k t constant, proportionality constant, into psi r hat into I q s. So, torque is totally along the torque is given by this expression. So, torque can be controlled by controlling the torque component of the current IQS only, keeping the flux constant at the rated value, psi r at the rated value one way, and for high speed operation IQS is kept constant and rotor flux psi r is varied to give high speed operation. So, torque sensitivity is the highest and response is very fast, and torque per current is also maximum. So, these are the features of vector control. Next, we will discuss salient features of this vector control. In vector control drive, the frequency omega e, that means which will decide the speed of the drive, frequency omega e of the drive is not directly controlled. As in scalar control, the machine or the motor is essentially self controlled. Where the frequency and phase are controlled indirectly using the unit vector. Because unit vector comes from theta e and omega e, the synchronous frequency is d theta e by dt. So, this unit vector controls the frequency and phase of the current indirectly. Machine is in self control mode. So, another feature is there is no fear of instability. there is no fear of instability by crossing the operating point beyond the breakdown torque which is Te max as in scalar control. In scalar control, there is a fear of crossing the breakdown torque and hence in instability condition, but in this case there is vector control, there is no fear of instability, limiting the total current What is the total current? Total current is IS peak is IDA square plus IQA square root over. So, limiting this total current within the safe limit this limiting automatically limits the operation within the stable region. Within the stable region. So, in scalar control drive, if the breakdown torque is exceeded, then the motor will lose stability, become stops, but in this case the current components IDS and IQS are controlled in vector control drive. So, when we control IDS and IQS and thereby we limit the stator current, which is square root of IDS square plus IQS square, limiting the total stator current within the safe limit, will automatically limit the operation within the stable region and torque below the maximum torque. So, in this vector control drive, the transient response is very fast compared to scalar control. So, fast transient response is a great boon. So, like a DC machine, speed control is possible. In 4 quadrants, without any additional control element. Without any control element, like phase sequence reversing. In forward motoring condition, if the torque if the electromagnetic torque Te becomes negative, that means we can make Te negative by reversing IQS or flux through inverter control. So, if the Te becomes negative, the drive initially goes to regenerative braking mode. Drive goes to regenerative braking mode, which slows down the speed. At 0 speed, speed reduces to 0, the phase sequence of the unit vector reverses through unit vector. That means, at after 0 speed, the theta e changes to minus theta e, opposite sign. So, phase sequence reversal is obtained. Thus, giving reverse motoring operation. Next, we will go to discussion of voltage model based flux estimation. So, voltage model, in voltage model we use stationary reference frame, or which is the alpha beta frame. Stationary reference frame is the two phase frame or alpha beta frame. So, in stationary reference frame, the equations, voltage equations I have already written earlier, explained. So, V alpha S is R S I alpha S plus d psi alpha S by dt. I alpha S is the stator current component and psi alpha S is the stator flux components, and V alpha is the voltage component, and also V beta S voltage component along the beta axis is R S I beta S plus d psi beta S by dt. So, there is no omega E related term, speed related EMF term, speed EMF term. So, from these two equations we get the flux psi alpha S, which is integral of V alpha S minus R S I alpha S dt, and psi beta S is integral of V beta S minus R S I beta S dt from these equations. So, with this you can prove and derive that the rotor flux psi alpha r equals to L r by L m into psi alpha s minus sigma L s I alpha s, and rotor flux component psi beta r is L r by L m psi beta s minus sigma L s I beta s. So, this is psi alpha and psi beta r are the rotor flux components in two phase frame which we want to estimate, and this is the equation you use, and here sigma is the leakage coefficient, that is 1 minus L m square divided by L s into L r. So, you can derive the rotor flux equations as I have written here. I will show you derivation in the next slide. Before that, you understand how the voltage model estimates. First, voltage model uses voltage sensors, two voltage sensors and two current sensors. Are used. Two voltage sensors and two current sensors used. So, from that we using the stationary reference frame transformation, we get V alpha s and V beta s from the voltage sensor data, and from current sensor data we get I alpha s and I beta s data. This is the step 1, we use voltage sensor. Step 2, we get V alpha s, V beta s, V I alpha s, I beta s components from 3 phase to 2 phase transformation. Once we get V alpha s and V beta s, we get third step, we generate psi alpha s and psi beta s. We estimate using psi alpha s and psi beta s, these two equations. Okay. Once you get psi alpha s and psi beta s, fourth step is we get psi alpha r and psi beta r is the fourth step. How we get? Use psi alpha r using this equation and psi beta r using this equation. So, using these equations we generate rotor flux component psi alpha and psi beta r for computing the unit vector as you derived previously. So, this is the algorithm. Voltage sensor, current sensor data are taken, then 3 phase to 2 phase transformation is applied to get V alpha s and V beta s, I alpha s and I beta s. From these data we get estimate the flux component psi alpha s using this equation and psi beta s using this equation. Once we get stator flux components in alpha beta frame, we get rotor flux component psi alpha r and psi beta r using this equation. Because we have psi alpha s, psi beta s, I alpha s, I beta s, we generate the rotor flux component psi alpha and psi beta r, which is used to compute the unit vector. Now, how you get the psi alpha and psi beta relation, you can work out yourself. I will just give a reference short derivation of one equation. So, you have L r by L in the right hand side, we have L r by L m into psi alpha s minus sigma L s into I alpha s. In the first equation of the rotor flux I alpha, we have this equation in the right hand side. So, let us expand this. So, L r by L m psi alpha s is L s I alpha s plus L m I alpha r. I have already explained it previously, minus sigma L s I s term is there. So, this is equal to L r by L m. So, L s into 1 minus sigma LS into 1 minus sigma into I alpha s plus Lm into I alpha r. That is Lr by Lm, Ls sigma is 1 minus Lm square divided by Ls by Lr. So, 1 minus sigma is Lm square divided by Ls into Lr into I alpha s plus other term is Lm into I alpha r. So, Ls cancels. So, Lm is taken outside. So, Lr into Lm1 Lm is taken outside, Lm into I alpha s plus sorry. So, Lm by Lr, let us write Lm by Lr I alpha s plus I alpha r. So, you have I alpha r. So, you have Lm I alpha s plus Lr into I alpha r. So, that is psi alpha r. So, we wanted to derive psi alpha r. So, psi alpha r is this, which is given by this expression for estimating. So, this is the derivation of the previous equation. And further we have the electromagnetic torque. T E given by 3 by 2 P by 2 Lm by Lr psi alpha r into I beta s minus psi beta r into I alpha s. This is the electromagnetic torque used from voltage model based estimation. In voltage model, we get the I alpha s, I beta s data from the sensor, estimate psi alpha and psi beta r, and using this expression torque can be computed. Next, we will discuss features of voltage model based estimation. Or voltage model based direct vector control. So, some of the features I will highlight. First of all, 2 voltage sensors and 2 current sensors are used. These are the sensor requirement, and this vector drive uses a current controlled PWM inverter. Because both flux and torque are directly related to current. The inverter, current control inverter, can have hysteresis band, PWM current control, or synchronous frame current control. Another feature is any error in the unit vector or distortion associated with the feedback signals will affect the performance of the drive. This method of vector control this method of direct vector control, which is using the voltage model, this will fail to give decoupling or vector orientation at very low speed. So, starting from rest with this method, is not possible. So, zero speed and low speed operations are not possible. The reasons are like this. At low frequency or low speed means low frequency, V alpha s voltage components, V beta s are very small. You can apply the same logic you applied in the V wave control. So, when the frequency is less, voltage will be small also. So, because voltage V alpha s and V beta s are small, ideal integration, we are integrating these equations. So, ideal integration becomes difficult or impossible, you can say, because of DC offset. Then another point is parameter variation. Which parameters? Stator resistance, stator leakage inductance, rotor leakage inductance and mutual inductance. tend to reduce accuracy of the estimated signals. At higher speed, and higher speeds means higher frequency, effect of parameter variation, can be neglected. So, conclusion is this vector drive, this direct vector control using voltage model is not suitable for industrial drives requiring starting from rest on low speed operation. So this is not suitable, voltage model is not suitable for low speed operation or drives requiring starting from rest. Next we will go to direct vector control using current model for rotor flux estimation. So, we have already derived V beta R is rotor voltage in beta component, R into I beta R plus transformer EMF is d psi beta by dt and rotational EMF is minus omega R into psi alpha R. The V beta R equation, and also we have the equation V alpha R, which is R into I alpha R plus d psi alpha R by dt plus omega R into psi beta R. These are the two relations. And also we have for motoring operation, as the rotor circuit is closed, V alpha R is 0, V beta R is 0, because rotor winding has to be closed for motor operation. So, V alpha R and V beta are 0. With that, using in the first equation, we have d psi beta R by dt, because V beta R is 0, d psi beta R by dt is omega r into psi alpha r minus r into I beta r. So, it is omega r into psi alpha r minus r by L r into L r into I beta r. So, that is omega r into psi alpha r minus r by L r I beta r is psi beta r minus L m I beta s. So, you can reorganize the terms equals to r L m by L r I beta s plus omega r into psi alpha r minus r by L r psi beta r. So, this is d psi beta r by dt is given by this. Similarly, we can write for the from the V alpha equation, we can write d psi alpha r by dt is r L m by L r I alpha s minus omega r into psi beta r. Speed related term will be negative because it is a 90 degree minus r by L r psi alpha r. Only omega r speed related term will be negative sign. So, in this case, in this current model based estimation, I alpha s and I beta s are obtained from current sensor data after transformation, 3-phase to 2-phase transformation, we get I alpha s and I beta s are obtained. Speed omega r is also sensed, speed sensor is there. So, once we get I alpha s and I beta s, so we get d psi alpha d psi beta r by dt because we have I beta s, we have, and using the same equations, you see. So, we start from initial condition with psi, initial value of psi alpha r at t equal to 0, psi beta r at t equal to 0. We start from the initial and we have the initial value of psi beta r, initial value of psi alpha r, and we have the I beta s, and using this equation we get d psi beta r by dt and update psi beta r k plus 1 is psi beta r k plus d psi beta r by dt at kth time into delta t. So, we update psi beta r using this algorithm. Similarly, we will update psi alpha r also using similar equation. So, because we get psi alpha, we have I alpha s, psi beta r and psi alpha r, we get d psi alpha r by dt, and also it applies to psi alpha r, we update it like this. So, using this current model, we estimate the rotor flux component psi alpha r and psi beta r. for generating the unit vector. So, estimation accuracy in this case is affected by the variation of machine parameters. Particularly rotor resistance, RR. But main advantage is drive operation can be extended to 0 speed. So, low speed operations are possible, even operation at 0 speed is also possible. That is the main advantage of current model based vector control. It can give starting from rest and low speed operation. So, it is preferred for industrial drives better than vector control. So, thank you for attention.